Hi, everybody. Welcome to today's session of the Spectral Geometry in the Clouds seminar. Today marks the 50th edition of the seminar, and it's been great to have you all to talk about spectral geometry during the last year. And it's I've really liked being able to do that to mark the time as this weird year has been going on. So today, we will have Maciej Zworski from Berkeley, who will talk to us about internal waves and homeomorphism of the circle. So the floor is yours. Thank you very much for being here.
Okay, well, thank you for inviting me. And I feel bad because I haven't really participated in this seminar much, but one of the things about COVID is that we could all sleep in if we wanted to. So 9 a.m. in California seemed like awfully early now. Normally it wouldn't have been, but so thank you. I will talk about a spectral theory problem, which is motivated by fluid mechanics. So here is the experimental setup, which is an aquarium where you have you can change the geometry of this aquarium. So this aquarium has a cross section, which is a trapezium, and then there's some forcing mechanism which forces some oscillations. And this is how the experiment looks. And what happens is as you sort of force this liquid, stratified liquid actually, through these oscillations, what one sees that there is a place where the velocity gets higher, which is on this geometric shape here. You can see this, there's basically a rectangle in this case. And that happens for certain frequencies and for certain geometries. So what you have here is, you change the slanting of this wall, you change the frequency, and you will see something different. So you can see that it's becoming more and more pronounced, this shape here. I hope it's visible everywhere. And this was actually predicted by very sort of nice and simple analysis by oceanographers, Maas and Lam, 25 years ago or so. And if I understand the history correctly, people thought that this would never be observed experimentally because, there are all sorts of other effects, etc., etc. But actually, it was, because I think there was a group in Lyon that had an aquarium with no fish in it, and they were able to conduct this type of experiment, and they saw what you just saw, the prediction of Maas and Lam being realized. And there is still activity in physics and many interesting questions about internal waves. So this is a sort of idealized situation in which you have this nice model of internal waves, but the motivation, if I understand correctly, comes from understanding currents in the ocean, and in that case the oscillation might be the tides produced by the moon, I suppose. So I will really talk about the mathematical model. So here is just I will not even read this. I copied it from a physics paper. There are various models for understanding, stratified fluids. I will use a linearized model, the basically Boussinesq equation, but I won't write it. I will use the following approximation that I learned about from a paper by Colin de Verdier and Saint-Raymond. But it was also before discussed by Ralston and by physicists. So this is a thesis of Brouzet, has a very nice account of this. And so basically we are going to consider the following simple equation, which looks a little bit like the wave equation, but in a sort of weird way, in the sense that dt square is followed by the Laplacian. And then you have a second derivative in x2. So we are in 2 dimensions. And there is some region in the plane, bounded region. I will give conditions on this region with a 0 boundary condition. And this is just the Laplacian. And the velocity, supposedly, in this model is given by curl of u. And so one would like to see where does this become singular or big or somehow manifest itself physically. And so this is really the question that one can ask mathematically. How do the frequency of the forcing term and the geometry of omega affect the solution of this equation as time goes to infinity? So this is the equation. And in the physics literature, it's actually posed as a spectral problem. And I will explain why this actually makes sense. Namely, you consider actually the sort of eigenequation, if you like, for this problem. And this will become more clear in a moment. So well, the purpose here is to discuss the long time behavior of solutions of this simple looking, but at first weird looking equation. But this is sometimes actually this is called a Poincaré problem, or maybe this equation is called the Poincaré equation. I am not a specialist. But here is the simple wave evolution equation. And let's say with 0 initial data. And here is an example of a square of size, of unit size, or maybe pi, sorry, size pi. Sides are of length pi, which is tilted by an angle, and you force it by a frequency. Well, here it's 0.7, and here it is. The solution looks like this as time goes on. So it sort of, does its stuff. But then what happens is that you see that you have oscillations with the singularities of u. I mean, U is smooth, or H1 at least, but some singularities appear exactly on this geometric shape. And that's sort of what you saw in the aquarium. And the idea is to understand this phenomenon mathematically. And so this is the mathematical model, and this is a spectral theory seminar. So we will take a spectral theory approach. Which is the following. You actually can consider the following operator. So this was the operator considered by Ralston, 50 years ago. Namely, we will take the Dirichlet Laplacian on our domain omega. So that takes you from h-1 to h10 functions which have gradient in L2 and 0 boundary data. And this actually turns out to be a self-adjoint operator from h-omega to h-omega with respect to the norm, which is basically inherited from just taking absolute value, gradient, integral of gradient square with this isomorphism here. Whoops. So P is bounded, self-adjoint operator, and the spectrum of this operator easily seen to be the interval between 0 and 1. And my problem here, the equation, evolution equation, is equivalent to the wave equation for this operator P. And you just take U to be the Laplacian inverse of W when you solve this equation here. But of course, this P now is an operator which in some sense is a 0th order operator rather than, the Laplacian. And of course, you can write down the solution to this equation. That's like calculus problem. And this is the solution with 0 initial data. You just apply the spectral theory to construct this operator. And then you can consider the following thing. You can look at the limit of this t form as t goes to infinity formally. You do this integral. I mean, this integral is again integrable by methods of calculus. And then as time goes to infinity, first you actually do the integral. And when you do the integral, you get this expression here for v of t. W is the real part of that. And then if p were, or p plus, the square root of p plus minus omega were, a variable, then this actually converges to this. This is just, if I thought in the sense of distribution as time goes to infinity. So a natural question to ask then is, the first question to ask is, do those limits exist? So in other words, we are interested in the limiting absorption principle for the operator P. And of course, that is related to continuity of the spectrum. And then one would like to understand what is the structure of those limits, and then using that to describe the asymptotic behavior of the solution. So sorry, I somehow lost. Oh yes, so there is a natural classical dynamics associated to this problem. Sorry, I need to move because which is this. Well, we could look at the eigenvalue equation for the spectral parameter lambda, and that of course is essentially, if I divide by the Laplacian, it's essentially this equation here. If you look at P is equal to P is Laplacian inverse times this. So at least formally, this is the equation that is equivalent to the eigenequation modulo this taking Laplacian inverse. And that, of course, is just the wave equation where you would think about x2 as time, x1 as space, and c this thing obtained from the spectral parameter as the speed of light. And consequently, there is a very simple dynamical system that is associated with this, and that's basically what was studied by Maas and Lam 25 years ago, which some people now call chess billiard. I kind of like it, even though I don't quite understand what it has to do with chess. But you're only allowing travel along lines with slopes plus minus 1 over c. So basically, the light race for this. So this is how this billiard works. You see, you just go like this. But for this trapezium, you see that for this specific value of lambda, what you have is this nice attractor, which is actually a rectangle. And the map, if you like, the diffeomorphism of the circle, or diffeomorphism of the boundary of this trapezium, takes a point on the boundary. You then move by a line with a slope minus 1 over c, and then you move by a line with a slope 1 over c, and you end on the boundary again. And that is a nice homeomorphism, which I will call f of theta of the circle. And so this is the dynamical system which is associated to this PDE problem. Though of course one has to make this connection rigorous. So this is, I recall, the chess billiard. You take a point on the boundary, you move by minus 1 over c, and then you go plus 1 over c. And this was, as far as I know, first considered by Fritz John in a kind of a quirky paper in 1941, where he studied the Dirichlet problem in the plane for the wave operator, for the wave equation. So it's natural why this appears there, I think. And then Ralston studied the same thing, motivated by the problem of rotating fluids rather than internal waves, but the same equation was modeling that. And it was actually also, it appeared in the work of Kolmogorov and Arnold. And in sort of a review article of Arnold said that actually considering this was his entry to dynamical systems. And that, I'm not going to go into this, but that led to a solution of the Hilbert's 13th problem for continuous functions, which in plain language says that functions of 3 variables do not exist. And just as a little sort of comic relief, I remember when Arnold first time came to the US in I guess 1990 or something like that, he gave these lectures in which he basically said, well, everything was done in Russia before, etc., etc., etc. But here is one counterexample. This map was actually considered by Fritz John before it was considered by Arnold in Russia, who was the first in Russia by his own account. So that's the way it is. And of course, then it was considered by Maas and Lam. And there is also actually a paper with Deustermatt on this, and they consider Lyapunov exponents and rotation numbers, and their motivation came from internal waves. And there were other works of the recently work actually motivated by chess. That's where the name chess billiard comes from. And actually just this year, there is an interesting paper by Lenci and his collaborators that discusses the existence of attractors and other things for this model, for trapezia and for other domains. So I recall that we have this map which takes, this point on the boundary, you move by the slope -1/c, then 1/c, and you end up back in the boundary. That's the dynamical system. And this is a homeomorphism of the boundary of the circle, if you like. And in our problem, eventually it will be a diffeomorphism. And Poincaré in 1885 associated to such homeomorphisms the rotation number. So rotation number is obtained by taking a lift of f from a map from the circle to the circle to so orientation preserving. This is actually an orientation preserving homeomorphism to an increasing function on the line f tilde. And then remarkably, so this n here means nth iterate of this map. This limit exists and is independent of x that you took. So it's a simple analysis exercise, but a very neat one. And a remarkable property of this map is that the periodic orbit hitting the boundary 2p times, like this rectangle that we saw, is equivalent to rotation number being a rational number with qp coprime giving the row. And this rotation numbers behave in an interesting way as lambda varies. It's a decreasing, the way I define it is a decreasing continuous function. So it's sort of like a devil's staircase. And here is a picture of devil's quarry, namely you take rotation numbers as functions of lambda, and then you change the base of the trapezium to be 1 plus b. And what one sees is that one has this large rational plateau. And in fact, Lenci and collaborators proved existence of such plateau for more general things than trapezia. But for trapezia, you can see there's at least for some configuration of sides, it's not difficult to see that you have rational things. So just some review of facts about this classical dynamics. In our work, we will make the following assumption, namely that omega is smooth. So corners are causing a lot of trouble in the analysis of this boundary value problem, at least to us. I at first thought corners would be easier, but at the end, it turned out that I was afraid of something in the smooth case, but it turned out that it's actually not difficult. So if you like, we put some caulking at the corner of the aquarium, and it's now a smooth boundary. So the kind of simple to state assumption is that omega is convex, and it is, for say lambda, fixed lambda, it is strictly convex at points of tangency with those lines, the characteristic lines with those slopes. And the slope is given by this, and it's assumed to be typically, this assumption may not be satisfied for all, will not be satisfied for all lambda, but it will be satisfied on some interval. Even in my picture of devil's quarry, as you can see, my lambda here was not going from 0 to 1, but from 0.2 to 1. And there's a weaker assumption that's a little more technical to formulate, so I will not state it. So as I said, it's essentially classical that this is continuous and monotone, this function, and that you have a hyperbolic attractor of lambda naught. Hyperbolic attractor here simply means that I have my map F, I have a periodic point, and so Fn has a fixed point, and the derivative of Fn at that point is different than 1. And once you have this hyperbolic attractor for lambda naught, then this is stable. It will persist for lambdas in a small or larger neighborhood. If this map is constant, then the constant is rational. And we have finitely many hyperbolic attractors almost everywhere on the interval where it is constant. And what's important for existence of domains with these properties is that if hyperbolic attractors exist for a domain with corners, then they also exist for a smooth rounding of the domain. So you just round off the corners, and that's useful because we can use existence of hyperbolic attractors from simpler models to know that they persist in the models to which the PDE analysis applies. So as I said, that one question that one asks here is the limiting absorption principle, namely the existence of these limits here. And indeed, these limits exist, and they P is this operator, which is dx2 squared, the second derivative squared, times the inverse of Dirichlet Laplacian. These limits exist for lambda, which satisfies the dynamical assumption that I stated. This maps C infinity with compact support inside omega to H minus 3/2 minus. And well, here is the actually the operator P again. So the Hilbert space on which one works is H minus 1 actually. And this, as I said, the dynamical assumption is open. instead of hyperbolic attractors being orbits, you can also have fixed points. And in fact, that's a sort of a generic situation. So they considered numerics in the case when you have fixed points. And in that case, there's some progress in the second paper by Colin de Verdier, but the situation is not as neat and not as understood as in the case of these hyperbolic attractors that are closed orbits. And another thing that motivated by the physics literature that Jeff Galkowski and I considered was the following problem. Namely, you take this operator, which is zeroth order operator on the torus, and you add to it the I times nu times the Laplacian. And that supposedly is a model for adding viscosity to the problem. Now, this problem, P plus I nu times the Laplacian, that now is an elliptic, for nu positive, it's an elliptic operator of order 2. So it has discrete spectrum, of course, non-real, it's a non-self-adjoint operator, but it certainly has discrete spectrum. And it turns out that near a point lambda, where the dynamical assumptions are satisfied, namely hyperbolic attractors exist, the eigenvalues of this converge to the discrete set of resonances, if you like, of this zeroth order operator P. So this was based on an adaptation of the methods of Elfer-Chestrand and Chestrand in the study of phase space study of quantum resonances. And actually there's related work by Geddes, Bontonneau, and Jezequel, which actually would allow to do this for more general manifolds. So I will just show a picture. So we see this is a picture where this is the real line. These stars here are embedded eigenvalues for this problem. The dynamical assumption is satisfied for lambdas here. And this is how the eigenvalues of P plus I nu Laplacian move as nu goes to 0. And this is seen in a movie. So here they move, and then they move faster. They somehow speed up as nu goes really to 0, and boom, they converge to these guys here. And here the dynamical assumption is not satisfied, and I did not, I actually don't know what happens there mathematically. We did not really go there, but what is the structure of the spectrum is not clear. And actually, Jian Wang also discussed the dynamics of viscosity eigenvalues. So you see, when I look at this picture, I somehow thought that something weird happens as nu goes to 0, because they all seem to like suddenly, after this very slow motion, they seem to speed up at the end. But actually, there's nothing crazy. It's a smooth thing, and the derivative of the eigenvalue of this operator at an embedded eigenvalue at nu equals to 0 is equal to like minus of the imaginary part is minus the something obtained from the embedded eigenvalue, the Laplacian applied to the embedded eigenvalue. Square, L2 norm. That's right. In this case, the Hilbert space is L2. So just a slow digression, because there are some open problems here about this viscosity limits. You know, one question, this is actually, I got interested in this because of a question by Liverani, which was that suppose you take an Anosov flow on a manifold, you add to it this viscosity term, it turns out that the eigenvalues of that converge to Rouel resonances. So this again is an elliptic operator. So, and there were earlier results for Anosov maps. And just like in our situation, results are not valid when the dynamical assumption is not satisfied. This type of result is false for non-Anosov flows. So this, what I'm showing here, is the limit set as nu goes to 0 in the case when X is the generator of the geodesic flow on the cosphere bundle, circle bundle of the torus. So you need the dynamical assumptions. And this is based on exact or complex WKB analysis of this operator due to Galtsev and Shafarevich. And actually, I knew about this, that the chemists were using sort of something called the complex absorbing potential method to calculate resonances. But it was actually this model, so technically it's different, but somehow morally it's the same, is to consider the Schrödinger operator, or more general operators. But an open problem, which I find maybe it's esoteric, but I personally find very frustrating, is that I don't know what happens if we are not in the Euclidean case, but in the case of asymptotically hyperbolic manifolds, where you have resonance and everything, but such things, there's no analog we could come up of this moment. And Alexis Drouot used a more natural way of adding this viscosity term in the case of geodesic flows on manifolds, and then by adding something called a spherical Laplacian. This is no longer an elliptic operator, but it's hyperelliptic. So again, you have discrete spectrum, and again, it converges to resonances. And there was also very interesting work of Dank and Rivière, who proved that this viscosity limits being Pauli-Codruel resonances for gradient flows, in which case this viscosity term after a conjugation becomes the famous Witten Laplacian. And in fact, it was first done for the height function of the sphere by sort of explicit calculation motivated by some high-end physics by Franco and company. So I just want to, I'm not going to go, too much into the proof, but just give some indications of the proof. So it's important. So we are interested in this limiting absorption principle and the singular structure of the limit. Well, so the natural parameters here are the frequency omega squared, that would be the real part of lambda. And then there's some small imaginary part. And we have this speed of light, which is given by this formula here. And as I said, we make this assumption that the geometric assumption about omega and the dynamical assumption that we have these hyperbolic attractors. And this was the operator to study. So for lambda with epsilon positive, with a positive imaginary or non-zero imaginary part, this is an elliptic operator. And so we actually, this has a very easy factorization. I'm not going to write it, but you can imagine what it is. And what one does, when epsilon is positive, this is an elliptic operator. When epsilon is zero, this is a hyperbolic operator. And what happens is that somehow this factorization shares the feature of the factorization of the wave operator, just in the standard way, but also factorization of the Laplacian as dz and dz bar. And these operators here, when epsilon is positive, have features which are the same as dz bar. And we actually use the analogy with holomorphic functions to prove estimates for the boundary value problem, which are uniform with respect to epsilon. It's roughly speaking, it's sort of, maximum principle, does not depend on sort of your epsilon in your dz bar operator, roughly speaking. So this factorization is important here. And then we consider, this elliptic bound for epsilon positive elliptic boundary value problem. So because it has a solution, a unique solution. And then we follow again the strategy which is well known, namely reduction to the boundary. The only thing about this now is that the boundary. Normally in an elliptic boundary value problem with a zero boundary condition, the reduction to the boundary is an equation for the normal derivative of the function at the boundary. Well, here it's a little more complicated. There is a normal derivative, but there's a prefactor, and the boundary is characteristic, namely that at 4 points where we have tangency of those lines to the boundary, the this vanishes. This vanishes. So this is zero. So it's not just a normal derivative. But nevertheless, despite this complication, one can do the analogues of single layer potential theory with this V, and for instance show, for instance, that if this V is smooth, then the solution U uniformly with respect to epsilon, then the solution U is smooth also uniformly with respect to epsilon. And this V now satisfies an equation. This is not the equation that my honest V satisfies, but I will give a simplified version just to indicate what it is. It satisfies the following equation. V is equal to T epsilon V plus G, where G is smooth. This G comes essentially from solving, comes from the forcing term F. And then you solve it, and you get some smooth function restricted to the boundary. You have a smooth function, so that's this G. And then the structure of the sort of hyperbolic structure, if you like, of the operator gives this T epsilon as the following Fourier integral operator. So this is, roughly speaking, its principal part, which is just a pullback by some diffeomorphism of the boundary K, and then you cut it off to positive frequencies. So this chi plus is a smooth cutoff for psi positive. So we're in one dimension. Huh? And then there is a term which is regularizing. So this term is actually smoothing. So in the elliptic boundary value problem, we would just have V equals to G. Essentially, this would be smoothing, and V would be smooth if this smooth if everything is. But the issue is uniformity with epsilon, because that's the limit. So this is the operator, and K is a diffeomorphism of the circle with two fixed points. So this never occurs in our situation, but this is just meant as a model. Has two fixed points, and one is repelling, one is attracting. So certainly such things exist, and are easy to write down. So two fixed points, and you have this operator. And actually, the study, I mean, it's not the same. It's different, but a study of pullbacks and estimates on them has a long tradition, dynamical systems, but it's a little different here. But nevertheless, it's always there's some similarity. And what you do is this is close in spirit to the work of Four-Roy-Chestrand. What you do, you find a weight, and you conjugate your operator by this weight, and this weight, roughly speaking, behaves like some function on the circle times log of absolute value of psi. So this is a pseudo-differential operator, and it has the property of this sort of growth along the flow, so to speak, or here it's a map, discrete flow. And the estimate, which somehow is in spirit similar to the estimates from dynamical systems, is that we can bound the L2 norm of Tg of W by a small constant times the norm in L2 plus some constant. So this should have been C1, I suppose. Oh no, sorry, C1 is here. C1 is positive, but in a weaker space. So this and for good G, so these G's have to satisfy more properties than just this. But you can construct G's for which this is true, and you can have properties of this G which give you various consequences, such as that V is in H minus 1/2 minus. So for this, the structure of the prefactor in this FIO is important, and V is smooth away from the attractive fixed point, and much more. So this Lagrangian property, in this case, it's conormal. It's in one dimension, so it's quite simple. So this is kind of somewhat superficial account of this, showing that this V has singularities which are exactly at the points, fixed points periodic orbit of our map. And then from that, the analysis based on this factorization that I mentioned shows that in fact we will get smoothness in the interior except on this Lagrangian obtained from these points. And then the strategy is the same as the strategy we used in a paper with Dyatlov before. So let me conclude with some open problems here. The first problem, which we did not address, but is kind of a curious and frustrating problem, is what is the spectrum of this simple operator away from the rational plateau of rotation numbers? We show that there, it's absolutely continuous when the dynamical assumptions are satisfied, which is satisfied almost everywhere on this rational plateau. But what is this spectrum away? Is it, and Ralston made some contributions to that. I think under some assumption for a tilted square, he showed that you can have eigenvalues of infinite multiplicity. And I don't know whether the spectrum is pure point. My kind of naive conjecture would be that it is actually pure point dense, but I don't know. So you see, is it always absolutely continuous or pure point? Could there be singular continuous spectrum? Yes, so as I said, there could be infinite multiplicities. Now, the second question is that, is there an analog of viscosity limit in the setting of bounded domains? That, you see, we studied this with Galkowski in the case of the torus, the model of the torus, but in the physics literature, it's more natural to consider it for bounded domains. And probably the right way to do this would be reduction to the boundary. But we have not yet addressed this. So as I said, these are the references in the physics literature for this type of problem. And now what happens for domains with corners? Well, as I said, that corners turned out to be nastier. One of the nasty things about the corners is that we, in the setting that I described, we actually have smoothness of the solution except at this singular set. But when you have corners, that is no longer true. There will always, not maybe always, but generically, singularities which emanate from the corner, but they are weaker. They are not in H1/2, they're better than H1. They're like H3/2, roughly speaking. But it's I mean, I don't know what really happens in the case of corners. And then the other question, which is sort of maybe, you know, again related to the physics literature, do those quote-unquote resonances, those limiting eigenvalues in the viscosity going to zero, do they manifest themselves in reality? And that's a kind of a tricky question to address in general for quantum resonances. But in this case, the reason is that using spectral theory will always have some contribution from parts of the spectrum where the structure is different than on this nice, absolutely continuous bits, and that those things will produce some long-time effects, masking the exponential decay from resonances. So I don't know whether there is a way to see this. Yes, so this, as I said, that this is open even here. So in the Euclidean case, for quantum resonances, we typically have a, say, semi-classical parameter, which allows us to see the effect of quantum resonances, modulo, say, H infinity or something like that. And of course, the question is what happens for more general manifolds. And then you have fixed points. As I said, there was partial progress by Colin de Verdier, but the picture is not quite as neat and clear. And here maybe those numerical results of Nigam and her student would help. And of course, there is a question of stability and instability due to nonlinear effects, because after all, this is a linearized model. But I have not, it's hard to extract a statement of equal clarity from the physics literature as those statements that we were discussing here. But clearly there are some interesting problems here and plenty of physics literature on that, but I haven't seen a statement that was kind of appealing to a pure mathematician. So to conclude, I have to say that this problem is kind of neat because you see classical quantum correspondence or particle wave correspondence in an experimental setting, which you also see numerically and prove it. And in some sense, many aspects of dynamical systems, microlocal spectral theory, are reflected like in a little drop in this setting. So I will conclude now. So thank you very much for your attention.
Thank you very much, Professor Zworski, for your talk. And it is time now to take questions. So if you have questions, please just unmute yourself and go ahead and ask your questions.
Yes, I have. It's Colin de Verdier. I have a question and two questions, in fact. Do you study the case where the domain is non-convex, but with a strict convexity at tangency point or concavity or strict concavity?
Well, we don't. So you see, we make an assumption. We call the domain lambda simple, and you can have examples where you have non-convexity. So this lambda simple assumption says that if we take, you see, if you factorize this operator for lambda real, you have two L plus lambda L minus lambda. Then you look at the dual form of that. And that gives you two functions. You restrict those functions to the boundary, and you see each of these functions has exactly two non-degenerate critical points. That's the assumption. But that, of course, will allow potentially non-convexity in other places. And this is the actual assumption that we use, the lambda simplicity. I just didn't want to introduce more vocabulary. But you can, but that assumption, we need something like this. This non-degeneracy at those points is what saves us from the horrors of the characteristic boundary, because it's a characteristic boundary value problem as epsilon goes to 0 at those points. But somehow the strict convexity, meaning strict the non-degenerate maximum or minimum of these functions, gives us still a nice structure of this operator, the T analog of this T epsilon that I showed before.
Okay, I have, in fact, two other questions. In case of corners,
yes,
it's possible that corners are attractors. Point are
that's right. That is correct. Yes.
And did you do something in this case?
No, we did not. I actually have to say we did spend quite some time thinking about corners, because at first I was so afraid of this characteristic boundary value problems. I thought corners will be easier. But somehow, these corners, I don't know, maybe we missed something, but we did not. Of course, they are attractors, and you see this like even in the movie. You saw that at some places when there is a special configuration for lambda, the line just goes between corners, for instance. That can certainly happen.
Can I mention?
Sorry?
Hi, this is Simon Dyatlov here. So when we have this lemma that says that if you have a domain with corners and you can smoothen it out to have one where the assumptions still hold, we explicitly assume that the closed trajectories do not intersect corners. So for smooth domains, you can check that there cannot be a hyperbolic trajectory that goes through glancing points. For domains with corners, it could happen. And so when we do the smoothing thing, we explicitly assume it does not happen. So, yeah.
So I have still another question, if I can. It's if you take the case where the domain is an ellipse, or the interior of an ellipse. In this case, you can prove easily that it's integrable. It means you have a continuous family of caustics. And so there is a problem like Birkhoff conjecture. Are there other domains for which you have this integrability for each value of the speed of C? That's a nice question.
Yes, that's
maybe it's easier. Maybe it's easier than.
No, but I'm suspecting, you know, I think a simpler example than the ellipse is a square that's not tilted.
Yeah.
In that case, you have the dynamical is, it's also completely integrable in some sense, you know, the square.
Yeah.
And you know, in that case, the rotation number is a smooth function, 1 over 1 plus c, if I remember correctly. And but the spectrum, none of these interesting phenomena occur in that case.
Okay, but
So,
it's a question of
oh yeah, no, it's a natural question to ask. Yeah, but this you see, I have
some
to say
people
that,
are interested in billiard, so it's
yeah. Well, yes, but this is yes. No, so I don't know about the ellipse.
okay.
What people study, you know, I believe in the paper maybe with Doistermaat or other papers by Maas and Lam, they studied the case of a half an ellipse, you know, or half a parabola or things like that. They because in that case you do have these attractors, etc., at some values of lambda, but I haven't thought about the ellipse to be honest.
Okay, thank you for your talk. It was very nice.
Okay, thank you. Good to see you, Yves.
You have paper on archive now, or
no, not yet. We are finishing
okay.
now. You know how it is.
You send me a mail when.
Oh yeah, of course.
Okay, thank you.
Yeah.
Thank you. We have time for more questions if people want to ask questions or comment. And if not, I propose that we thank our speaker again. Thank you very much for this nice talk. We will see each other again next week for a talk by Misha Karpukin, who will speak about stability of isoperimetric eigenvalue inequalities. So June 7 next week, same time, same place. Thank you again for your very nice talk, and be safe, everyone. See you next week.
Okay, thank you. Good to see you, everybody.